All right. In 20, I am asked how much will a certain function change, the function e to the x cosine yz, when I go between 2 points, the origin, which I'm going to call p, 0, 0, 0, and q, which I am told is away from the origin a distance of 0.1 units in the direction of 2, 2, negative 2. So away from the 2, 2, negative 2. Okay, now that's not what I'm going to move to. I have to move in that direction, so in the direction of the unit vector. So I should divide by every one of these components by the magnitude of the position vector of q. And let's see, 2 squared plus 2 squared plus 2 squared is 4 plus 4 plus 4 is 12. That's the length squared, and so the length is the square root of 12. I need to divide everybody by the square root of 12 here. Now that is a point, a distance 1 away from P. Now I need a distance 0.1 away from P. So I need to multiply all of these components by 0.1, and so I'll just replace all these 2 with 0.2s. 0.2s divided by the square root of 12. Okay, so the change delta f in this function between that point and that point is, let's see, approximated by the equation. Let's see, delta f is approximately. Now I'm going to give this all to you all at once. The gradient of f at 0, 0, 0 dotted with, and here's something much more general, PQ. The vector from P to Q. All right, take a look at this equation for a second. If I had df dx times dx, right, df dx, the rate of change of f with respect to x times some x interval, or rise divided by run times run would be another way to think about it. Rise divided by run times run, that would be an amount of rise over this amount of run. But we have multiple directions that we're moving. All of the directions in PQ, the direction in the first coordinate, the direction of the second coordinate, the direction of the third coordinate. And so we've got to separate all of these things out. Okay, so that is, we're going to take as dot product because we want the rate of change in the x direction times the distance between the x coordinates here plus the rate of change in the y direction times the distance between the y coordinates here, etc. This is only approximate because you should think of this as part of the linearization. Okay. Notice that I got another complaint about the textbook. I did not include any differentials in here. I didn't say df this time. In 19 I talked about df because that is what the book wants you to think of. Okay, it wants you to think of df as the change in f. But of course df should be an infinitesimal. For me, delta f and df mean very different things. df is infinitesimal, delta f is the change in f, and I have always kept those things separate in my mind. So, delta f, the change in f, not an infinitesimal thing, but a macroscopic thing, is this dot product. Let's go ahead and evaluate this. Now, I write an equal sign here. It means that is going to be equal to. Right? That's always the thing from the end of the previous line that's matched up with the equal sign. Okay, the gradient of f, that is the gradient of f. Derivative with respect to x of that will be just e to the x cosine yz. Next component, derivative with respect to y. Well, that won't touch the e to the x. Then I'll have the derivative of cosine, which is sine, with a negative sign. And let's see, the derivative of the inside with respect to y. The derivative of yz with respect to y is z. So I'll have a z right there from the chain rule. Next, derivative of that with respect to z won't touch the e to the x, but I will be taking the derivative of cosine to get a negative sign. And the argument stays just as it was, but the derivative of the argument with respect to z is y. Good. And then I need to evaluate that at 0, 0, 0. And then I need to dot it with PQ, and that is simply 0.2 over square root of 12. Oh, I shouldn't have done that. Now I have to write the square root of 12 and all the components. I should have factored it out. Right, I should have factored out 0.2 over square root of 12 from all of these, put it over there. It would have saved me some writing. Then I could have just had 1, 1, negative 1 with a 0.2 over square root of 12 out there. All right, so the next thing to do is to evaluate this vector here at 0, 0, 0. That is, all right, e to the 0 is 1, cosine of 0 is 1, so that's 1. I got a z right there, so I put in a 0. That's going to be 0, and also 0 there with a y. Dot that. Now, this time I will not make the same mistake. Let's see. I need to put 0.2 over square root of 12. Hey, wait a minute. Isn't square, let's see, 12 is 4 times 3, so I could factor out a 4 from all those 12s. And the square root of 4 is 2, so I could cancel a 2 up there. That is 0.1 over the square root of 3. 0.2 over square root of 12 is 0.1 over square root of 3. So let me keep that point right there. And dotted with 1, 1, and negative 1. Which is, oh, well, okay, the second two components go away, and this is 0.1 over the square root of 3. Okay, let me make sure that I am fairly proud of my wording. The change delta f in the function, this function, between this point and this point is, now this is a general formula, the change in f between any 2 points P and Q, where P is near Q, is the gradient of f evaluated at P dotted with the vector PQ. Okay, is approximated by the change in f is approximately this, which is equal to this, which is equal to this, which is equal to 0.1 over square root of 3. Yeah, I'm pretty happy with that sentence.